Let's compare the difference between y equals f of x versus what if you have x equals f of t and y equals g of t. First of all, y equals f of x. This is the graph of a function. That is, for each x, the value of y is computed from f of x. Let's look at a brief example. You have y equals x squared plus 3, or in other words, here, this x squared plus 3 is a specific example of what the f of x would be up here. So in this example, f of x is x squared plus 3. You know what to do with this. When x is equal to 4, for instance, you'll get y equals 19, and you would plot the point 4, comma 19. And if you picked a different value of x, well, you'd plot a different point. The difference here, when you have two things, you have x equals, and then there's an expression involving t, and there's y equals and another expression involving t. This is called parametrization, or a parametric curve. So for each t, the value of x is computed from f of t. Notice the difference up here. The value of y was computed from f of x. And the value of y, the second thing is to compute the value of y, and y is computed from g of t. So example, x equals what's shown in red here, 2 cosine of t over 4 plus cosine of t, and y equals 2 sine of t minus 3, for example. So if you plug in t is equal to 0, x will be 3, and then plugging in t equals 0 into 2 sine of 0, I guess, for t minus 3, you'll get y is equal to negative 3. So you'll plot this point 3 comma negative 3. So plugging in t equals 0 gives you x is 3, y equals negative 3, and you get this point. You notice in this point, it doesn't actually, you don't see the 0 right here. And let us show what this looks like. So there's a link. I'll click on this, and we will bring this up over here. All right, so what we're looking at is, first of all, on the left, there's a t-axis here, and then this vertical axis is both either an x or a y. So what you see is, as t moves along, along the t-axis, t is about 3 right now, you get, let me try to sort of hold on to this here. Let's go back to when t is equal to 3. So when t is equal to 3, 2 cosine of 3/4 minus cosine of 3 ends up giving you 0.47. And when you plug in t equals 3 into 2 sine of, well, 3 here, minus then a 3, you get negative 2.718. And so when the time is 3, x coordinate is about a half, y coordinate is about negative 2.5, and you get this one point right here. So this point shown in purple. And then when t is a little bigger, you'll notice that the x value has decreased slightly and the y value has decreased slightly, so you get this point that's a little more to the southwest. Okay, so let's see if we can retry playing this. I guess I'll just have to drag this along. And you'll see that at each value of t, we compute, or rather, of course, the computer's computing this, but it's getting a, for 3.27 for t, it's getting a value of x that happens to be 0.376, and a y value that happens to be negative 3.256. Okay, and let's just keep increasing t, and you'll notice, in fact, this curve that we have here happens to intersect itself. That's just a coincidence that occurred. So starting from, let me just reload this. So we'll see the animation occur, hopefully. Yep, there we go. This nice slow animation that as t moves onward, you see what point the point shown in purple shows you that value of t. All right. So just some comments about the example we saw. You can think of t as being time. In fact, I think I already accidentally slipped that in. So for each value of t, evaluating 2 cosine of t over 4 plus cosine of t tells you the x coordinate. And for each value of t, evaluating 2 sine of t minus 3 tells you the y coordinate. So as a possible interpretation for what's going on, for each moment in time t, maybe a bug or a particle, an atom, an electric particle or whatever, is located at this point here. I'm using that same color coordination. So this point that's shown in purple right here, maybe that's how a bug travels. Just a bug is on a plane, right? That plane could just be like a table, right? And so you're just watching this bug travel in this sort of loopy fashion. These coordinates could tell you, like, right at, what is this, 4.2, so 4.2 seconds at that moment of the experiment, here's where the bug is located. And then at 5.4, seconds, the bug is located at 1, negative 4.4. Okay, the vertical line test does not have to pass. We see this in the example we were just looking at over here. And just to provide another interpretation, I don't know if you've played with this old toy called the Etch-a-Sketch. It has 2 dials, and one dial controls the x-coordinate, one controls the y-coordinate. And that's what you could think of this formula that is background highlighted in red and the other highlighted in blue. You could think of it like that. So again, you have t as being time, and this first formula is what tells you the x-coordinate, or rather it tells you how far that first dial might be wound clockwise or counterclockwise. And for each value of t, this second formula, 2 sine t minus 3, tells you the y-coordinate, and back to the Etch-a-Sketch interpretation, this would be how far the second dial is wound, whether clockwise or counterclockwise. And so the interpretation here would be that each moment in time, t, the toy paints a specific point, and that point again would be just the same as where the bug would have been located. So in a typical Etch-a-Sketch drawing, the vertical line test does not have to pass. So imagine 2 people who are not looking at the Etch-a-Sketch. Each person has control of one of the Etch-a-Sketch dials, and they kind of both go randomly. And if they're not coordinating with each other what the picture would look like, it's very unlikely that the vertical line test would pass. Okay, so we'll take a look at another parameterization here. So x equals 2 to the t plus 2 cosine of t squared minus 25, and y equals 2 to the t plus 2 sine t squared minus 25. And we're only going to consider t values between negative 10 and 10, so let's click on that and see what we get. You'll notice in this, the point is moving around very rapidly at first and kind of slows down, and then, the movement is more rapid. So the movement doesn't always have to go at constant speed. Like that part right here is very wild and rapid. You can imagine that a bug got caught in some, vortex of like a fan whirling around or something like that. Or maybe there's a bug that was caught on a spider web, and so just because the fan was blowing at a certain intensity, the bug just kind of, while stuck to a spider web, is moving around in what appears to be a circle to our eyes, and kind of got loose eventually and kind of escapes away or something like this. Okay, this could again be the motion of a bug. A bug starts moving quickly at first in what almost appears to be a perfect circle, though it's not quite a perfect circle. And in this example, when t is near 0, the bug moves slower, and then a wind to the northeast, let's say, starts to pick up. So we'll go back and look. Let's observe right around when, so t is negative 7, negative 6, negative 5. Let's look when t is around 0, like right around now. Yeah, the movement's kind of slow. And that's all just built into how this the formulas for x and y look. There's also 3D parameterization. So same general idea, where 2D parameterization is when you give a value of t, there are 2 separate formulas. One called f, one called g, that give the x-coordinate and the y-coordinate. Now that there's a third coordinate in the third dimension, we need a third formula that we've called h of t here. So at each moment in time t, the point f of t, comma, g of t, comma, h of t describes the location in 3-dimensional space of a very small object. It could be a bug. It should really even be smaller than a bug, but think of like the centroid of a bug or something like that. So for example, in a pot of boiling water, you drop a single pea. Just that vegetable, and see how does that p move around. So f of t could describe the x-coordinate of the centroid of the p at time t, and g of t could describe the y-coordinate of the centroid of a p at time t, and h of t could describe the z-coordinate of the centroid of the p at time t. So for instance, at time t equals 8, the p is located at f of 8, comma, g of 8, comma, h of 8. So the path that a pea travels in a pot of boiling water doesn't have to pass anything like a vertical line test, though graphing x versus t does. So if you looked at this and there was a t-axis, I guess, and then the f-axis or the x-axis, that would have to pass the vertical line test. Graphing y versus t has to pass the vertical line test, and graphing z versus t would also have to pass